For this third and final question of exercise 1 on rainfall losses, we are not going to calculate a global loss like it was done in question 1 and question 2, but we will only calculate the infiltration losses. We will do this based on the Green and Emd method and actually also the Mine and Larsson scheme, which includes the Green and Emd method. We need to consider a couple of characteristics of the soil, like the hydraulic conductivity, K, moisture content deficit, M, and a capillary pressure head, phi. This phi is not the same phi as in the previous question, where it was the phi index to calculate the global losses. Here it is the capillary pressure head. Now, as you might remember from our theoretical lectures, the Green and Emd method gives you an approximation of the infiltration rate. Therefore, we need 4 main assumptions. We should have a soil that is homogeneous. We should have a sharp infiltration front, as shown on the picture. And we should have a uniform moisture at the start, and above the infiltration front, the moisture content is saturated. It's theta S, which is the saturated moisture. Now, if we look back at the Mine and Larsson scheme, we should always keep in mind that we should actually work with intervals. And that's also what we are going to do during this exercise. So we start always in our scheme here at the top, and we go down, first asking questions about the initial part of the interval, afterwards also projecting it to the end of the interval. And the first question is actually if the infiltration capacity is smaller or equal to the rainfall intensity, yes or no. If the infiltration capacity is smaller or equal to the rainfall intensity, it's clear that at the start of the interval we already have some ponding, because not all the water that falls as precipitation can actually infiltrate into the soil. We can calculate then the ponding over the complete interval by using the Green and Emd method, and we end up again at the start of the next interval. Oppositely, if we don't have infiltration capacity that is lower or equal to the rainfall intensity, we actually have more capacity than the rain that falls, and everything will infiltrate specifically now at the start of the interval. So that's what is mentioned here. And then we can calculate some tentative values, because there are 2 options. As we start with all water that can infiltrate at the start of the interval, it can happen that either during the whole interval there will be no ponding, so the infiltration capacity will remain higher than the rainfall intensity, or since the infiltration capacity will decrease when there is more infiltration, it can be that at the start of the interval the rainfall intensity is still lower than the infiltration capacity, but at the end of the interval this might be different. There might be not sufficient infiltration capacity, and ponding might start somewhere in the middle of this interval. And depending on that, so we need to calculate how much water there could infiltrate at the end of the interval, calculate the infiltration capacity, and then we can check if this condition is true or not, if we're in either one of these 2 cases. And depending in which case we are, we or have everything that is infiltrated during the interval, or there is ponding starting from a certain point in the interval, and then we also need to apply the Green and Emd method like before. Let's check out the formulas again. The formula of Green and Emd for infiltration capacity is given by this formula. So it's K, the hydraulic conductivity, multiplied with 1 plus M multiplied with phi over Ft, the total amount of infiltration, of infiltrated water. M, phi, and K are given, so it's just a case of calculating the infiltration capacity and the total volume of infiltration. If we integrate that, we also get a formula to calculate the total volume of infiltration, but we should look out because this is also depending on the amount of infiltration itself. So we might need an iterative calculation step to find out how much water there actually infiltrates. Also, the previous formula that was given here is actually when we have no infiltration at the start of the interval. So there was no infiltration before. But if we do have some infiltration already before, we need to apply this formula, which is based on the same formula, but then combined for the beginning and the end of the interval. Now, we still don't know what the formula would be if the infiltration capacity is still higher than the rainfall intensity. And there we actually use just this formula, which says that the total amount of infiltration at the end of the interval is equal to the amount of infiltrated water at the start of the interval plus all the water that falls as precipitation, because we actually assume that everything is infiltrated. In case there would be ponding during the interval, there are methods to calculate the time of ponding, Tp, which will be somewhere in the middle of the interval, and we know that before we have full infiltration, so we can actually use this formula, and at the end, after Tp, the time of ponding, we need to apply gradient. And a way to calculate that is by these formulas, because at time t is Tp, we actually know that the infiltration capacity is exactly equal to the rainfall intensity. And in that way, we can calculate the value of Tp. So that's the theoretical introduction to this part. I have come up already with a part of the Excel sheet that we are going to use, where I filled in still the area that was already given before. I have here the K value in centimeters per hour as it was given, the M value 0.16, and the phi value in centimeters 5.4. I also gave here the precipitation in millimeters, and I added the formulas that we should use for this exercise. So now let us first start calculating the values all in the same units. Let's go to millimeters per hour for the hydraulic conductivity. As before, since this was in centimeters per hour, we actually need to multiply by 10 to express it in millimeters per hour. Similarly for phi, we need to multiply it by 10 to get it into millimeters. We can also calculate the rainfall intensity, also in millimeters per hour, as we did it before, by multiplying this by 2, since we have intervals of 30 minutes. If we would have intervals of 60 minutes, we would only multiply it with 1, so the value would be the same, since then it was really in millimeters per hour. So but to get the rainfall intensity, we multiply here by 2. Let's drag this to the end, and so we get the value that we need. Let's make this a little bit more clean, like that, and like that. Now, as I said, we should now work with the intervals of the Mayen-Lassen scheme. The first thing we need to know is the amount of infiltration at the start of the interval. So that's capital F, and it's expressed in millimeters. At the start of the initial interval at time 0, there was no infiltration so far. We assume that it was dry, the previous storm was long ago, so the initial amount of infiltration is 0. The infiltration capacity that corresponds with this value of 0 at the start of the interval will be calculated based on this formula. But as we see, the infiltration amount is in the denominator. Yeah. So if we divide by 0, we would get actually, in this case, an infinite infiltration capacity. Let's put this here with a symbol. Here it is, like that. So it's infinite. Now, this means actually that at the start of the interval, our infiltration capacity is higher than our rainfall intensity. So at the start of this first interval, all the water that falls will infiltrate. So we're actually, if we go back to the minor Larson scheme, let me go quickly back to that. We're here in this case that we say no, because our rainfall intensity is smaller than our infiltration capacity. So we calculate, as it is done here, the tentative values for the end of the interval. So we say Ft plus dt, that's the amount of infiltration at the end of the interval, expressed in millimeters. And since we have an interval of half an hour and an infiltration capacity of 6.6, we actually say this multiplied with 0.5. Half an hour, this is expressed in millimeters per hour, or we could have taken here the precipitation volume as well. So at the end of the interval, tentatively, we would have a total amount of infiltration of 3.3 millimeters. We can calculate also the infiltration capacity that corresponds with this amount in millimeters per hour based on the formula given here, so the green and M formula for the infiltration capacity, and therefore we will need to use our coefficients, our parameters that we had for this soil type. So it is K multiplied with, and then we open the brackets, 1 plus, we open the brackets again, M, and we take of course the millimeters because everything is expressed in millimeters or millimeters per hour, multiplied with, oh, I took M already, that was wrong, so it's M, multiplied with phi in millimeters. We close this first bracket, divide by this value, Ft at the end of the interval. We're looking at T plus dt, and we close this bracket as well. So this gives us a value of 144.73. And this 144.73 is still higher than the 6.6, which is a constant rainfall intensity during this interval. So if we go back to the minor Larson scheme, we're actually in the case where we have no ponding over the whole interval. This also means that this infiltration capacity at the end of the interval and the infiltration amount at the end of the interval is also the actual infiltration amount at the start of the next interval. So we put this here because that value is the same, like that. Now if we compare the infiltration capacity at the start of the second interval with the rainfall intensity during this interval, we see again that we don't have ponding at the start of the interval because this is bigger than this one. We can calculate then again the tentative amount of infiltration at the end of the interval, and therefore we will actually add up. I should take it from this one, doesn't really matter, but it's better to do it in this way. So we take the amount at the start of the interval and we add the amount that actually falls during the interval. So we get an amount of 9.9. The corresponding infiltration capacity can be calculated by using the Green and Empt formula again. So we say this one multiplied with 1 plus this multiplied by this divided by our F value, and we close the brackets. So again here we see that we have a value of 74.91 millimeters per hour, and that is still higher than the amount than the rainfall intensity, for this interval. So we have ponding, no ponding over the whole interval. As before, we can just copy this like that, because that will be the start of the next interval, the third interval. But then we see that actually we have 74.91 millimeters per hour as infiltration capacity, but this is lower than the rainfall intensity. So we're here in the case where we have ponding at the start of this next interval. Now we should use the Green and Empt formula and not the basic formula, the tentative one here where everything infiltrates. So we should use the Green and Empt formula that is mentioned over here. Yeah. Since our Green and Empt formula contains F2 in both the left hand side and the right hand side, and it is within the logarithm here that we have the F2, this cannot be calculated immediately. F1 is known and all the other parts are known. So also here this F1, that's the amount of infiltration at the start of the interval. So but to calculate F2 we need an iterative procedure, or we can use the function of Excel which is called goal seek. This function can be found in the what if analysis tab. So we go to data, what if analysis, and there you can find the goal seek function. This is a Dutch version, but in English it will be called goal seek. Now to do that, if you would go to goal seek, you see that you can find a certain value for the cell. So we want here, for example, in an intermediate calculation, G16 to become a certain value by changing another cell. So how can we do that in this case? Well, we need this formula. Let's say that we calculate our formula in here. So F2 is equal to, and that would be F1, the value at the start of the interval, so the amount of infiltration at the start of the interval, plus the hydraulic conductivity multiplied with the time of one time step, so for the whole period, that's 0.5 hours, plus m multiplied with phi, multiplied with the logarithm, and let's open up another bracket, of m multiplied with phi plus our value of f2. Let's say that the value of f2 is also mentioned here. Now it's still empty, but we will need that. And we divide this by, and we open up the brackets again, m multiplied with phi plus f1, the amount at the start of the interval. If we calculate it like this, taking into account that we take an f2 value, d20 here, of 0, we get 23.30. Now, the way to do that is actually now to bring f2 also to the other side. So we know that this is f2, and the value here at this moment is also f2. But if we subtract this value from this formula here, we get actually that 0 should be equal to, and then we have this formula, right? At the moment that still remains 23, but if we use the goal-seek function and we say that this one should become 0 by changing the cell D20, yeah, that's where we had the second F2, so this F2, and we also did minus F2, we actually are going to try to get the result of this formula, which includes the value here, close to 0, and that would give us a value of f2 in this cell. So let's do that. You will calculate that automatically, yeah? And we get a value of 0.000 something, very small, so close to 0, with a value of 37.84. We can try this. Let me take this formula. Yeah, that's the formula that we just used before. So without subtracting the f2 value. So we look at the formula here. That's actually the one that we used here. So f1, that's here, this value, plus k, the hydraulic conductivity, multiplied with 0.5, m multiplied with phi, multiplied with the whole logarithm here, which also looks at the f2 value here. And then we should get a value now out of this formula that is almost equal to 37.84. And that's correct, 37.84. Of course, there is a small error, but that's really, really small. So we can take the final value during that interval of the infiltration amount as 37.84. We can calculate the corresponding rainfall intensity at the end of the interval. Let me first fix those values, because if we drag, we need to be able to fix the values. Yes, and then this one, that's the one that should look at this. That's okay. So if we drag, oh, there is something wrong. Oh yeah, this one should have been fixed as well. So fix this, F4, drag this, and we see again that our infiltration capacity decreases as we expected. We can copy these two, because that's again the start of the next interval. So at the start of the fourth interval, we have already an infiltration amount of 37.84, and our infiltration capacity that corresponds with that is 49.13. Now this 49.13 is smaller than the 136.4, so we have bonding from the start of the interval. We need to do the same calculation as in the previous step, so we can use our goal-seek function here again. Yeah. So now we need to refer not to the start of the previous interval, but to the start of this interval. So let's drag this like this, and then we should have the formula here already. And of course now it's not correct. We want this to be E19 is 0 by changing this formula, and we get to a value that is very small, so that's good. We get to 61.38. Let's look here. We do the same formula, and that's indeed correct. If we fill in the F2 value here, 61.38, we get also by calculating the total equation 61.38. So 61.38. Let's drag this, and then we get an infiltration capacity of 45.63. That's based on the K value here, on the M and phi value, and on the corresponding infiltration amount. So now we know how much there was infiltrated during this interval, and we know that these are the values that are valid for the next interval, for the start of the next interval. And again, when we see our infiltration capacity of 45.63, this is lower than the infiltration than the rainfall intensity here. So again, we need to use green and ant, and we start by referring this equation to our infiltration amount at the start of the interval. We get a value now again that is too big, but we say goal seek, this value should almost be 0 by changing this value. And again, we get a value that is very small, and a value of F2 83.78. Let's check this. We don't refer to the start of the previous interval, but to this interval, and indeed 83.78. So that's our total amount of infiltration at the end of the 5th interval. The corresponding infiltration capacity is 44.30. We go to the next interval. At the start, we have the values that we had at the end of the previous interval. We have 44.13, and again, this is lower than the rainfall intensity at the 6th interval. Again, we apply the green and ant method. We don't look at the start of the previous interval, but at the start of the current interval. We apply goal seek to this one. It should become 0. And we get 0 by adapting the value here in D20. Okay, we get a value that is close to 0, so that's good. Let's try to refer to the correct cell here. And indeed, 105.61 is our infiltration amount. The corresponding infiltration capacity is 43.27. So we go to the final interval, and now we see that this 43.27, the infiltration capacity, is higher than our rainfall intensity. So we're getting towards the end of the storm. The rainfall intensity becomes smaller, and then indeed we see that we have sufficient infiltration capacity for all the rain to infiltrate. So we're again, here at the start of our Mayen-Larson scheme, and we go to the no side because our rainfall intensity is smaller than the infiltration capacity. So we start by calculating the tentative values. This tentative value, as we had before, would be the amount of infiltration at the start of the interval plus the rainfall intensity multiplied with the length of the period, and that's 112.21. The corresponding infiltration capacity will be 43.08, and this is still larger than our rainfall intensity. So we are here at this right hand side of our minor Larsson scheme. So you see that there is never, in this case, in our exercise, a point where we have ponding during the interval. We always had either ponding from the start of the interval or no ponding at all. Now we still can calculate here the losses. So actually I should say the actual infiltration per time step. Yeah, we'll call it losses anyway, in millimeters per hour. We cannot use this because that's the infiltration capacity. We should base ourselves on the actual rainfall, actual infiltration amounts. So in the first case, that was the amount multiplied with 0.5, no, with 2, because this is over half an hour, and we're looking at the intensities like this. For the second one, we could do the same, but then we have too much, of course. So we need to subtract those two of each other first. So we need to subtract the amount at the start of the interval from the amount at the end of the interval, and multiply this also by 2 to get the intensity. So in this case we say 9.9 minus the amount at the start, and that multiplied by 2. So that's 13.2. Everything will be infiltrated at that time. And that was what we knew also, because we did not have ponding here. We can drag this towards the end. And this is correct, because here we also see the infiltration amount at the end of the interval minus the infiltration amount at the start of the interval multiplied by 2 to get to millimeters per hour. So we see that not everything infiltrates here in these time steps because we had ponding, yeah? And it's also not equal to the capacity. It's another value, it's the actual infiltration losses. And then we can calculate the net rainfall, also in millimeters per hour. Let's make this a little bit nicer. Subscript. Okay. And now our net rainfall is, as the definition said, the actual precipitation minus the losses, and that is our value. We do that for all of the time periods, and then we see that indeed we get our net rainfall. And at the start we have a net rainfall of 0 because everything infiltrates. Then there are some time intervals where we do have net rainfall, and the time intervals where we had ponding, and then in the final one it's already again infiltrating completely, and we get 0 again. As before, we can make a graph out of this one. So let's say we take the time, we take the losses, and we take the net rainfall. We create a bar graph. Let's move this graph 3. Let's change the colors. Losses are at the lower side, so that's good. Let's change this color here to orange, and this one to our blue color that we had before. We add access titles. This will be time in minutes. And the other one is, the other one is precipitation in millimeters per hour. What you can see from this graph is that indeed our infiltration capacity decreases over time as the amount of infiltration actually increases. Yeah? So this would be the line somehow of our infiltration capacity, because it decreases because there is always more amount of infiltration. If we compare those also with the previous exercise, for example here with 2.1b, the graph here, we see that also the smaller pulses, as in, for example, for the phi index, the smaller pulses are not generating any net rainfall, where this was the case for the runoff coefficient, yeah, like this. So that's a better representation, and then additionally this decreasing trend is also a more realistic representation. So that concludes this first exercise on rainfall losses. If there are still any questions, you can always go to the session that is organized either for the students in Leuven or in Brussels, where one of the assistants will be available for questions and answers.